Hi, my name is Tyson. Welcome to the Data Science 1 YouTube channel. This is my third episode. I'm very excited to share with you guys for another episode of Data Science Podcast. So let's get started. So before I do that, let me just quickly share my screen. Share screen. Okay. All right. So today's project podcast will be focused on ED admission case prioritization using a classification model. So before I begin, let me talk a little bit about myself. So I was a former business intelligence analyst at KMH and a strong advocate for machine learning enthusiasts right now, and the founder of the Data Science 1 YouTube channel. So from an education timeline perspective, I studied medical biophysics at Western University in my bachelor. And then after that, I took a research assistant job at Sunnybrook, working on the medical imaging for image processing and the radiation physics for the cancer treatment studies. And then after that, I completed my master's studies at University of Toronto, studying health informatics. And then from there, I took a corporate job at KMH, working on the business intelligence domain for quality assurance for data warehousing and the data visualization and reporting validation requirement with our stakeholders and the business user. So right now, these days, I'm kicking some side machine learning project for my own interest. So here is agenda on what we'll be covering today on this project podcast. So let's begin with the problem overview. So let me talk about the ED admission background in Ontario in 2017. So the usual ED wait time for initial assessment is 3 hours. And then the total time spent for the ED admitted patient is around 31 hours. And on average, emergency department visits annually is around 618,000 visits. And then finally, the average cost of the single ED visit costs around $260 per visit based on the 2008 figure stats. So why should we care about this problem? So there are a couple of important factors that I want to highlight. First, there has been an increase in incidence of adverse patient outcome in the emergency department due to high volume. Second, increase in emergency department wait time. Third, decrease in capacity to transfer patients into the inpatient beds. So the potential stakeholder for our project will be ED unit manager, clinician group, and the medical insurers, and others including family caregivers and the health policymaker. So the main goal of this project was to improve ED patient case prioritization by classification model with the two main objectives. First, prioritizing the urgent cases over non-urgent cases. Second, facilitate the management of ED patient flow. So now let's have a look at the overall data set. So this data set comes with the 30 input feature for predicting one output admission label. So there are about 16 categorical features and 14 numerical features. And then which includes information about the patient demographics and the diagnostic measures. The sample size of this data set is around 65,000 rows. And as you can see on this middle screenshot, there are patient demographic features, diagnostic measure features, and the one class label. So the major challenges of this project is there is a highly class imbalance ratio between different class label. Second, missing values on certain features. And finally, some outliers and the duplicates. So now let's talk about the data wrangling perspective. So here is the overall ED admission model workflow that I designed, which I can describe in two stages. Stage 1 is focused on model training and tuning. Stage 2 is for the final model performance estimates. So on the stage 1, first we load the raw data onto the Python as a data frame, then execute the data wrangling step, and then perform the data partition step to split the original data set into the training, validation set, and the test set. So on using a training set, we're going to build or train our model. Once the model gets trained, we're going to use our validation set to further validate and optimize our model parameters to get the best model. So once model is completely trained, we're going to use our holdout test set to evaluate our model performance across the different classification algorithm of our choices. So now, moving on to data wrangling overview. So there are 5 major steps involved in the data wrangling step. First, low data loading onto the Python. Second, executing the missing value replacement. Third, handling outlier to remove the outlier from entire observation. Then fourth, executing the resampling strategies to adjust the class imbalance ratio in our dataset. Finally, applying a feature transformation to convert the features into the different format or to generate a new set of features from existing features. So now let's talk about missing value replacement in more detail. So there are two main methodologies to deal with based on the scenario. So for example, let's say in our feature, we computed a missing value percentage on each single feature, and our threshold is 50%. So then if we detect any feature that's actually missing more than a 50%, we'll just simply drop them, because even if you imputated them, it's not gonna add any meaningful result or the value. So on the second method, we're gonna use a feature imputation technique using a measure of central tendency, such as mean, median, and mode, based on the type of the input feature we have. So for example, on this figure, you can see that the before imputation and then after imputation technique on our features. So for gender and ethnicity, like categorical feature gets replaced by the mode, and the numerical feature like average income and distance can be replaced by either a mean or median. But in some scenario, median is better because it's less subjective to the outliers. So now, moving on to handling outlier. So there are different methodologies to do outlier, such as interquartile range, standard deviation, z-score, and then linear model type of estimation. So on the right sub figure, you can see that here is a box plot of the average income. And on this box whisker plot, there are 5 important stats: are mean, median, max, and the fourth quartile and third quartile being 25th percentile and 75th percentile. And also notice here that on the red circle, you could see the outliers detected by a box plot. So based on this information, we could compute the interquartile range, which is simply a subtraction from third quartile minus fourth quartile. Then using this interquartile range, we can compute the lower bound and the upper bound threshold. So for example, the outlier will be treated as outlier, observation will be treated as outlier, for example, if any values sit below or above these threshold, they will be treated as outlier. We will just simply remove them from the entire observation set. So now moving on to resampling. So in earlier, I mentioned that our data set is highly class imbalanced because 96% of them are non-admitted cases, and only 4% of them are ED-admitted cases, which is a huge problem when we are training a model. So in order to adjust this problem, we're going to execute the resampling strategies. So basically taking the negative sum sampling on majority class level to make a sample size equal to the ED-admitted cases, so that the overall, the adjusted class label proportion being 50-50%. So it is also feasible to test different ratio, but in our scenario, I actually ended up testing the 50-50% to make them equal ratio. And also there's some other resampling strategy that we could test it. So now let's talk about feature transformation as a final data wrangling step. So there are 2 types of feature transformation. First is the feature scaling. So on a feature scaling, we are basically using a feature scaler function passed on to the setup input feature to standardize a different range of features into the similar range. So on this figure, you can see that the histogram of the average income distribution for ED patient, the only thing actually that changes is the x-axis, the ranges of the scale of the average income. So the second thing is the feature encoding. So feature encoding is basically we're converting a categorical feature into the numerical format. So as you can see on this table, the figure is representing the conversion of the ethnicity into multiple dummy variable by encoded as a 0 and 1 to indicate whether the value has occurred or not. So now let's talk about the exploratory data analysis of our data set. So first, here is the ED population in terms of distribution for continuous measure, such as average income, distance, and the symptom to visit days. So first, in terms of average income, the majority of patients seems to come from the low to middle income classes, And then note that here in the non-admitted patient, the distribution is extremely skewed to the right. And the second, in terms of distance, the major patient seems to live nearby hospital within ED admitted patients within a distance range of 100 to 200. But also notice that the non-admitted population seems to show the extremely skewed distribution to the right. And finally, in terms of symptom to visit days, so on an ED admitted patient population, there seems to be relatively short symptom to visit days occurring. And also notice the non-admitted population shows the distribution extremely skewed to the right as well. So now moving on to ED population in terms of patient demographics. So here are the two figures of the bar charts representing one for the gender ratio, the other one for the ethnicity. So in terms of gender, there are a higher percentage of male population than female patient in both population. And finally, in terms of ethnicity, the higher percentage of Caucasians found in both population. And the one thing that interesting to note here is that the higher percentage of Inuit patients within the non-admitted population compared to ED admitted population. So now let's talk about the ED population in terms of diagnostic factor. So here are the two pie charts for each group representing for the family history ratio and the allergy ratio. So in terms of family history, there seems to be 100% of patients who get admitted into emergency department had a family history, some kind of family history. Whereas in terms of allergy, the ED admitted patient seems to have a higher ratio of having being or allergic compared to the non-ED admitted patient. So let's talk about the diagnostic factor too, in terms of the mean GP visit, mean MRI count, and mean medication taken. So first, in terms of general practitioner visit, the non-admitted patient had a mean of 5 GP visits compared to the ED admitted patients, so about 5 times higher. And also in terms of MRI count, non-admitted patient likely done MRI exam 7 times higher than the ED admitted patients. And finally, in terms of previous medication, the non-admitted patients likely taken medication 5 times higher than the ED admitted patients. So moving on to correlation matrix. So here are the correlation matrix for before resampling and the after resampling. So the major thing that I want to highlight here is that there has been an increase in correlation among all numerical features after the resampling. So the first, the correlation of general practitioner visit increased from 0.49 to 0.73 after resampling. So the other thing to note here is the order of increase in magnitude will be followed by previous medication, MRI count, and etc. on other numerical features. So now let's talk about the model selection and the result of our ED admission problem. So in terms of model selection, I ended up testing 6 different classification algorithms of my choice. First is the logistic regression. Logistic regression is basically we're using a sigmoid logic function to transform the input feature value and calculate the probabilistic range as an output from 0 to 1 to separate the class label. And the second is a support vector machine. It's type of a marginal classifier interested in drawing a best decision boundary by computing the maximum margin between 2 hyperplanes. Works well on the linearly separable classes problem as well. And third is the k nearest neighbor algorithm. So we choose k nearest neighbor and count the number of data points on our region of interest, computed by Euclidean distance to assign every single new data point to relevant class label or the category. The fourth is the decision tree. Basically, it split the data on the choice of our features, then repeat the splitting procedure until each node left with the same class label. Fifth is the random forest. This type of ensemble learning model creates many decision tree. Then we average the performance of tree on each observation to assign different class label. Then finally, the gradient boosting, the XGBoost model, is type of a sequentially training classifier in a stepwise for fashion. So what it does is from each iteration, it learns the mistake, the residual error from previous model or the state to improve the overall accuracy in the final iteration. So now let's talk about feature selection. So here is the feature importance plot of the XGBoost classifier. The reason I chose XGBoost because it actually performed the best among other classifier. So the take-home message here is that among all the category feature we have, the top 10 selected features are the following. And then the top 5 selected features by XGBoost classifier are the test B, diagnostic test B, second average income, distance, general practitioner visit, and finally symptom to visit days as a fifth ranking based on the feature importance score. Now, let's move on to model comparison. So in terms of model comparison, like I said, I compare across 6 different classification algorithms. And based on, in terms of the model accuracy and then misclassification error rate, the best performing model was XGBoost classifier. So now, let's talk about model evaluation in terms of confusion matrix. So here is the confusion matrix of XGBoost classifier. So the interpretation here is that the 94% of correct predictions are made on the ED admitted cases and non-ED admitted cases. And there are about 6% of misclassification error rates were detected. So the take-home message here is that the balance between the machine learning model and the human intervention is required, especially to monitor the 2% error rate being the first negative, because in a clinical scenario, if you miss these patient group, this can lead to the adverse outcome. In a worst scenario, having an increased mortality rate on the ED emergency department unit. So let's talk about a model evaluation in terms of log curve and precision curve. So on the left figure shows the log curve of the 5 different classifiers that I tested. So the highest were the XGBoost logistic regression and the SB support vector machine model. So in terms of XGBoost, the area under the curves indicate the 0.98, meaning that about 98% of time, the model is good at separating the ED admitted prediction from the non-ED admitted prediction. And the second figure on the precision recurve curve of the XGBoost classifier suggests that the on average precision level is 0.97, meaning that about 97% of time, the model is actually good at making ED admitted prediction from total number of actual ED admitted cases. So here is the recap of our project. So the main goal was to improve ED patient case prioritization using classification model. And in terms of result, model was able to predict whether or not a case require ED admission. And then 94% of accurate predictions were made on the test set. And in terms of risk, the model incorrectly identified with 2% of error as likely they do not need admission, in fact, when they need it. So the mitigation strategy here is that to review, identify error cases with the subject matter expert before making a clinical decision. So the next step will be conducting a pilot study and making some model improvement. So here is the business investment return for having a good ED classification model. So first, I want to highlight some key statistics. For example, as I mentioned it earlier, that the single ED visit cost on average Ontario hospital is $260. And on annually visit, the ED visit is around $618,000. So the estimated annual spending on ED visit alone in Ontario is $161 million. And here is a really important stat that I want to highlight it is that according to some health study by Health Quarterly Ontario, the 1 in 5 emergency department visit in Canada can be treated at the doctor's office. So basically what that means is the estimated annual return on investment for having an excellent ED classification model, assuming that's actually working 100% correct, that we can potentially save $32 million that can be spent elsewhere in other healthcare system. So now let's talk about the future works and recommendation. So in terms of limitation, first, this was a simulation study, not based on the real data set. Second, the validity of study is, that's why validity of study is questionable with the subject matter expert. So for the future work, what I want to see is the conducting a pilot study at the institutional level with the real patient data set and making some model improvement on other, by trying other ensemble learning, like stacking, other type of boosting and bagging algorithm. And third, executing feasibility of different resampling strategy, such as smooth upsampling. And finally, in terms of model design, we could actually ended up designing a general practitioner visit stratified classifier. So one for our lower GP visit patient cohort, less than a 5 GP visit, higher GP visit patient cohort for more than a 5 GP visit, as an example. So in terms of recommendation, here are 3 recommendations that I like to make. So first is we can actually implement ED admission case prioritization guideline based on the evidence we gather from the EDA exercises. For example, the non-admitted patient compared to ED-admitted patient likely have 5 times higher general practitioner visit, 7 times higher MRI exams done before, and 5 times higher history of previous medication taken. And second, basically we need to set up a good data collection and integration infrastructure. So we need to integrate the EMR and all the administrative data records for every single patient. And second, inclusion of meaningful feature like triage category based on the severity of the ED admitted patient condition. Second, hours after ED admission in the past history for every single patient. And hopefully some other type of numerical or meaningful feature. And finally, conducting a pilot study. So I hope to see developing a proof of concept machine learning model and pipeline for the model deployment to be actually used in clinical practice and getting a feedback from a subject matter expert. So on my next episode, I want to cover web scraping project from Indeed.ca on the different types of job title, including data scientist, data engineer, business intelligence, and etc. So thank you for